Let's try to tackle this integral. There's going to be a lot of identities that are going to be used and a lot of relationships that we're going to have to exploit, but we are eventually going to get an antiderivative. So I see a 9 minus x squared there. That to me looks like the pattern a squared minus x squared, where the a is a 3. 3 squared is 9, 9 minus x squared. So this to me is going to read a sine substitution. So I'm going to copy down the integral exactly as it is. And my first step is going to be the sine substitution. A squared is 9, so my a is 3. And finding a differential here, I get 3 times cosine d, what I'm calling alpha. So I want to go ahead and replace everything at once. Let's say that the square root of 9 minus x squared, if I replace my x with 3 sines, this is 9 minus x squared is 9 sine squared. And by pulling out a 9 and then removing it from the square root, I have a 3 with a square root 1 minus sine squared, which we can recognize as cosine squared. And when we square root the cosine squared, we just get a cosine. So I can replace the square root of 9 minus x squared with a 3 cosine. So let's go ahead and do this. The x squared in the numerator is being replaced by a 9 sine squared by this relationship right there. The dx, also in the numerator, is being replaced by a 3 cosine d alpha by this relationship here. So dx is gone, the x squared is taken care of. Now for the square root in the denominator. We replace that entire square root of 9 minus x squared with a 3 cosine. And we see a lot of nice cancellation. The 3 cosines are gone, and we really just have to integrate 9 and sine squared. Now, this is still a head scratcher because sine squared does not easily integrate. But we can use a double angle formula and rewrite sine squared as 1 minus cosine of 2 times the argument divided by 2. So that's just us making use of the identity. Sine squareds of somethings are equal to 1 minus cosine of 2 times those somethings over 2's. So with this, we can use linearity of the integral and break this up as 9 times the integral of 1/2 minus 9 over 2 times the integral of cosine of 2 alpha. And now that we're here, an integral of 1/2 just becomes alpha. So we have 9 alpha over 2. And this, pause the video if you would like. It is a U substitution, but hopefully you can, you're at the point now where you're starting to recognize these U substitutions and can do them in your head. This is going to be a minus 9/4 sine of 2 alpha with a plus c. Okay. Last thing to do is just to go back and find how to replace all of these alphas with our original variable x. So let's think about this term here, the 9 alpha over 2. Well, I can use, let me get rid of my notes here. I can use this relationship and solve that for alpha and find that alpha is equal to the arcsine of x over 3. So this 9 alpha over 2 becomes 9 arcsine x over 3 over 2. And now let's zero in on this 9/4 sine of 2 alpha. So I've got minus 9/4. And we can replace sine of 2 alpha with the relationship that sine of 2y is equal to 2 sine y cosine y. So sine of 2 alpha becomes 2 sine alpha cosine alpha. And we see a little bit of simplification there. This becomes 9/2 arc sine x over 3 minus 9/2 sine alpha cosine alpha. And let's look back for relationships between sine alpha and cosine alpha. So sine alpha, by this top relationship there, is equal to x over 3. So we have 9/2 arc sine x over 3 minus 9/2. This sine alpha is being replaced by x over 3. And now this cosine alpha can be replaced by a 1/3 square root 9 minus x squared. Okay, now that's a good antiderivative. We don't have any more integrals to take, and we're back in the land of our original variable, but let's just clean this up a little bit. We have 9/2 inverse sine x over 3 minus those two 3's down there and that 9 up top are going to cancel, leaving me with just an x over 2 square root 9 minus x squared. And I believe I dropped my plus c here. So let's bring that back. Okay, so that is a good antiderivative.